Oh, okay. Are all of them simulated?
Yeah, all of them are simulated.
Okay, let's power this up and see what happens.
You want to do it now?
Yeah.
I get you the power supply. But you need to have the PC hooked up.
No, I don't want the PC hooked up.
No,
Just the
okay.
FlowNet box. We're covering the flow scan side of it, not the display side of it. You're the display experts, right? Do you have a little computer fan that we can blow air in through here?
Compressor?
No, not a compressor, just a small cooling fan. No?
Cooling fan.
I'll show you what I mean.
Oh,
You have-
I know what you want to do.
Right, you have strippers? Now, if we could get a fan to blow in here, we can put a total on it, and then I can show you how to do the calibration. So do you have a small computer fan or any kind of a fan?
There's anything rather other than
Yes.
fan. Fan is a difficult task.
See, or somebody can just go. So somebody can stand here and get lung exercises for a half an hour.
I have a fan, but
You have a fan?
this size.
Yeah, that's fine.
Yeah.
Because we can move it away
Yeah.
and get the flow rate.
Okay, he has a fan.
Good man. You're the best student. See, now, then I'll be able to show you how to actually calibrate it.
But I thought it came
No.
already calibrated.
The calibration is required because of the pressure spike pulsations and the volumetric fluctuations that the engine generates. Each engine is unique. Even the two engines of the same make, model, and horsepower rating.
So what Kuma tells me, it already calibrated. Isn't it calibrated?
All of it, understand is calibrated?
No.
Understand? No.
No,
No?
no, we have to calibrate. That's why Joe wanted me to, he sent you an email to show you how to do it. If we can get this reading here with a fan, then we'll be able to calibrate it. We might want to hold the, put it in the vise or whatever, but we'll see when we get the fan back. See, if we can get a steady liter per hour reading, whatever it is, then we can do the idle consumption adjustment. And then we can do the totalizer calibration. I'll show you how to do it.
So with this fan blowing, how much are we getting?
Well, I want to see anything from 5 liters an hour, 10 liters an hour, 15 liters an hour, something like that. It doesn't have to be perfect. But initially, maybe we can run it so it's faster, so we build up the totalizer quite a bit. Then we can back the fan off, and we can do the 2 calibrations that are required. The calibration is the idle consumption adjustment, which is done with the red switch, and then the totalizer calibration, which is done with the black switch. Just make it easier. Idle consumption adjustment, red switch, totalizer calibration, black switch.
Switches on the back of the meter.
Dip switches or rotary switches?
Deep switches.
That was an analog meter, single needle in it. Right, that's our old Cruise Master system.
Yeah, Cruise Master, yes.
That is a little more difficult to calibrate. The last 4 switches, switches 6, 7, 8, and 9, do the idle consumption adjustment. Switches 1 through 5 are the totalizer calibration. Most of the ships that you'll be dealing with will require temperature compensated systems, which you won't be using that gauge. It'll have to be either a digital gauge or the FlowNet gauge.
But most of the time we use the Cruise Master.
Do you?
That's the old.
Yeah.
Also, the Cruise
So far
Master,
the one all in Batam, they all use
Yeah,
Cruise Master.
but no problem. They are happy that.
They are happy because they doesn't know.
that Cruise Master is being phased out. It's a
Will they
very,
phase out?
it's very old. A lot of the
But they
manu,
wanted cheaper.
right. A lot of the
So we are not
manufacturers.
going to use that one anymore?
No more.
No more.
Okay.
So that one we don't have to go through.
No need.
Only this one.
Yeah.
Well, that one and also the digital gauges
Digital
too.
gauge.
Right.
So this one is important for us to know.
Right. This is our high-end system. Most of the bigger ships are probably going to want that, especially if they want the fuel consumption data transmitted to the home office, which will tie in with your electronics.
So how do I know this is accurate compared to the fuel consumption on the ship?
Well, let's say each engine has a dedicated fuel tank. And let's say you went out sailing the bright blue sea, and when you came into port, you refueled, it took 10,000 liters, okay? All right? If the flow scan totalizer says 10,001 liter, then it's accurate. You know, if it's within a couple of % of what it actually used.
They have to monitor it for a couple of hours. Let's say 1 hour, they calculate how much fuel they use.
Well, do they have the ability to sound the tanks and know exactly how much fuel they used?
I think they have
Sight gauges?
sight gauges.
Okay, sight gauges, as long as it's,
Maybe you can go through that with us.
okay. Well, on a commercial ship, there's a couple ways. There's what they call a sounding tape. With a sounding tape, it's like a tape measure tape.
Yeah.
And there's what they call a plumb bob at the
Yeah.
bottom of it, usually bronze, pretty heavy. You feed it down until it goes down and it hits a striker plate at the bottom of the tank.
This one okay?
Yeah, that would be perfect. Okay. Okay, it's starting to read. Let's see. Okay, yeah, we want this number to run up, so that's fine. Okay. Then when we do the two calibrations, we're going to want it to slow down a little bit. Okay, before I go into the sensors, I want to talk about filters and filtration. There's two filters on a diesel engine. There's a primary filter and a secondary filter. The primary filter is installed between the fuel tank and the engine. The secondary filter is mounted on the engine, and it's downstream of the fuel transfer pump or a lift pump. It is in between the lift pump and the injection system. The injectors, the injection pump, or the fuel rails for the injectors. Secondary filters are very fine filters. They're usually 2 micron, 3 micron, something like that. They're very fine so that they can protect the injectors from any debris scuffing the injector. Because they're on the pressure or discharge side of the fuel transfer pump, it doesn't matter that they're fine. A lift pump has no problem pushing through fuel through a very fine filter. It has a great deal of difficulty lifting fuel through a fine filter under partial vacuum. They call it a lift pump because most fuel tanks in a ship are in the bottom of the hull. We produce a partial vacuum. Atmospheric pressure pushes down on the top of the fuel, forces it through the fuel line up to the fuel pump. Most primary filters, most engine manufacturers want the primary filter to be a 30 micron element. They do not want a 2 micron or a 5 micron secondary filter element in there. What that does is it inflicts a life of hard labor on the lift pump. It will cause it to wear more quickly, age prematurely, and it also draws vapors out of the fuel. When those vapors are drawn out of the fuel and it goes through the optics in our sensor, the sensor reads it as an expanded fuel volume, just like air. So we don't want that. 30 micron elements don't do that. They're not hard. They don't make the lift pump work hard. 98% of engine manufacturers want a 30 micron element. So when you go to a ship and you're actually surveying the fuel system and determining where you're going to place the sensors, you need to check the fuel filter. You need to disassemble the primary filter housing and look at the element inside. The element will be marked with its micron rating. If it is a 30 micron element, that's great. But you need to also pull the element out and inspect it. If it's starting to load up and get dirty, you need to change it out. You need to replace it. When you reassemble the filter housing, you need to dry off all the seals and the sealing surfaces, and you coat all the seals with grease. a medium to heavy grease. Any type of grease is fine, the cheaper the better. You don't use a fine grease, you don't use motor oil, you don't use engine oil or fuel oil. The reason you use grease is because, well, first of all, if you looked at the sealing surfaces under a magnifier, you're going to see corrosion pits, you're going to see scrapes, you're going to see all kinds of defects. When you coat the seal with grease and you put the squeeze on the grease at reassembly, that squeeze forces the grease into those imperfections. Remember, a rubber seal or a Buna end seal, the rubber is not compressible. You're just squeezing it. So you get a good, solid, airtight seal. Primary filters are the major cause of air leaks or vacuum leaks. It's critical that you grease the seals. And when you do that, so you don't get oil and stuff on your hands, you can wear the vinyl gloves. Also, when you go to do these jobs, like I deliberately wore this outfit, you should have some kind of coverall or whatever to put over your clothes so it gets the diesel on it. Then your wives, or you can wash it or whatever, and you don't get it all over your clothes. Any questions? Well, that's basically it on the filters, but I can't stress how important it is that you verify that you have a 30 micron element and that you grease all the seals and sealing surfaces after you have dried them with a rag. No comments? Okay. Let's move on to the sensor assemblies. These are the parts of one of our high flow sensors. I don't have the sensor that's bolted to it. This is called the proportional bypass block. The majority of the fuel goes through the block. Only some of the fuel goes through the sensor. If you look inside of these, they have a little insert in there that pushes it down. If you look through this end, you can see it. And depending on whether it's a B, C, D, E, F, or G sensor, those inserts are a different size. This is an E sensor, so it's a fairly thin insert that's been pressed in. The fittings on that, or the threaded part, those are yet another type of thread. That's an SAE straight thread, or what they call a running pitch thread. A running pitch means that there's no taper on it, and it requires an O-ring to seal it up. The castings on the ends of the sensor, on the inlet side, we put on what we call a flow homogenizer. The canister inside the flow homogenizer, there's a tube with a bunch of holes in it. When fuel comes through the fuel line, there's a lot of turbulence with it. When you force it through openings or through small sections of tubes, it causes the flow to be more laminar. That means it's a straighter flow. There's less turbulence with it. That's important for our equipment because we want the fuel to impact the rotor consistently. If you had a lot of turbulence in the fuel, sometimes it would impact it harder, sometimes easier. You would get fluctuations. On our standard flow sensors, we don't have a flow homogenizer, but we have a flow straightener in there. That's a tube section. It has like 3 little openings in it, and it is very efficient, very effective at the lower flow rates that the standard flow sensor sees. That hex fitting, that flow straightener, is Loctited in place with the strongest Loctite known to man. If you rotate that fitting within the body of the sensor and crack the Loctite, you destroy the sensor. So whenever you put a fitting into that sensor, you always use 2 wrenches. One of the wrenches acts as a counter torque, and then the other wrench screws the fitting in. When you put it into the outlet port, you need to put a crescent wrench across the body of the sensor here, and then the other wrench to screw the fitting in. You always use 2 wrenches, one is the counter torque. If you don't, or if you put a wrench here and you put the fitting in here, and if you hear that Loctite snap, the sensor's dead. It's no good. You've destroyed it. And that's quite a common problem on these standard flow installations. Even though our instructions detail that, they still do it.
So you cannot break this no matter what.
Right, you can see that green Loctite. That's the
Yeah.
strongest Loctite made. And you have to make almost a real effort to break it. But if it does snap and you move that fitting even 1 degree, it's gone. It will not be, it'll still work, but it will not be accurate. Yep, you can hear the rotor spin up. This is the pulsation damper casting. This little tube in it is called a standpipe. When the canister is on it, it makes what is known as a standpipe accumulator. And in a fluid power system or a hydraulic system, the accumulator, the charge in it increases or it decreases, and it regulates the pressure of the fuel system. It takes out the pressure spikes. Ours works 2 ways. One, there's a membrane in that canister which absorbs energy. The second, we want some vapors, some gases, either air or diesel fumes trapped at the top of the canister. That gives a place for the volumetric fluctuations to go on the fuel transfer pump. Diaphragm pumps and piston pumps go up and down. And when they go up and down, a series of check valves have to open and close. Well, 2 lifetimes ago, when I took a marine diesel engineering course, old Professor Wing used to always say, nothing happens in no time. And what that means is it takes time for those check valves to close and seat. So when the pump is on the downstroke, a little bit of fuel will get by it. Having the vapor on the top of the standpipe accumulator gives a place for that very tiny amount of fuel to go to, so it does not impact the rotor and the sensor. Questions? You got to have a question. No? Anyway. So once everybody's looked at it and passed it around, we'll get the pieces back and we'll put it together, and I'll show you how to assemble the... So you don't really need to look at this. This is just a plain casting. The marine diesel fuel system, it's really a different type or another type of a fluid power system, and it obeys all the same laws as the hydraulic system does. Even though we're using diesel fuel as the fluid and not hydraulic oil, and it runs at low pressure, it still operates the same way. There are still control valves and filters and if you get into a situation out in the field where you can't get the pulsation damper in or whatever, you have to rotate the casting a little bit, either the flow homogenizer or the pulsation damper. We want the sensor to be pretty horizontal, and the sensor at the very bottom within a few degrees of rotation, no more than 5-10 degrees at the most. But to achieve that, you might have to rotate this casting a little bit. The pulsation damper and the flow homogenizer can be up to about 30, 35 degrees, even 40 degrees off center, and it will still work. To do that, you'll crack the jam nut or the lock nut that holds the casting in place. And when you reassemble it, you need to coat that O-ring with oil. It's very important. If you don't have oil in there, it can bind up. and pinch the O-ring, and then it will leak. You should not have to do this often. It should be avoided, but if you have to, you can. You just have to be careful. You also have to remember that these are aluminum threads, aluminum on aluminum. And though they're not pipe threads, you have to turn them slowly. If you turn them quickly, they can gall. And everybody want to come up here so you can see? You need to bring this casting so that that taper is beyond the threads, so that when the jam nut or the lock nut tightens up, it's pushing against this part and not the threads. So this would be down. Let's say we have to have it off a little bit. It's always better. See, the fuel will come in. This is the flow homogenizer. The fuel comes into the inlet port, exits the outlet port, into the proportional bypass block. If you have to do this, it's better to have a wrench of the correct size rather than a crescent wrench. Is this one bigger, or are they the same? Those are both the same. See, this one kind of barely fits in there. See, and then as you tighten it up, you can feel it bind. You should also, again, use 2 wrenches, but we can't here, so we use our hands. See, this wrench is kind of wide. It's hitting on stuff here. But you really, if you're going to be either doing the installations or responsible for it, you should have the tools. Even if somebody else does it, okay, a little bit skinnier. See, but also this doesn't have, it's not long, it doesn't have the torque, and it's not, and it is big enough. So here we would use a cheater. And then we set it. This has to be good and snug. You don't want to over torque it. You don't want to crack the aluminum, but it has to be tight. You don't want this thing to be able to vibrate and vibrate loose.
So what we see until the O-ring is actually compressed.
Well, O-rings won't compress. They squeeze. They're forced into the imperfections to prevent leakage, either air from being drawn in or fuel can come from coming out. Rubber is not compressible. You can squeeze it very thin and you can force it into all kinds of places, but it will not compress. You want to hand me that oil cup up there? Or where? Oh, never mind. Here it is. I'm sorry. On the other side, the pulsation damper goes the other way. So we lube up the threads. Lube up the O-ring. Right. Inlet, outlet, we're coming into the pulsation damper. And so let's say we want it end up like that. Wait a second, see, the sensor wants to be down. So let's say we have to have this off center differently than the flow homogenizer. This way we can use 2 wrenches. As fluid systems trainee, and you tried to assemble something with 1 wrench, the foreman would come by and wrap you on the knuckles with another wrench. And then you'd never do it again. Anybody want to try it?
Why does it have to go to the opposite side?
Right. The flow homogenizers always point down, but like I say, you can have it, up to 20, 25 degrees. You can go a little bit further, but we want to keep it no more than that. The pulsation damper, it's important to have it as perpendicular as possible against the block because we want to trap the maximum amount of air up there, the maximum amount of vapors or gases. We want that bubble to be as big as possible.
Oh. So
See,
this one has got to be straight.
pretty straight up and down. As you see, everything comes perpendicular.
Yeah.
If you have to move, if you have a choice of moving a casting, you should move the flow homogenizer. That is not as critical. This one you can do up to 15 or maybe 20 degrees.
So the color tells the difference?
Right, what calls it tell, but it's also, it says what it is. This is a flow scan flow homogenizer. This is a pulsation damper.
So, sorry, I don't understand this. When the oil
Comes
flow
in.
into here,
Yep,
it actually
it comes into here, it goes through that canister, then it,
go to the canister. Yeah.
right, then it comes into the block. Most of the oil goes through the block. A percentage of it, let's say 20%, I don't know what it is exactly, goes through the sensor, and then it joins back here, comes up, then it all goes up through the pulsation damper, comes into the body of the casting of the pulsation damper, fills up to the top of the standpipe, and then flows out. Hopefully we are pressurizing it a little bit, and we're trapping gases or vapors at the top of the damper.
Isn't this canister the same, or they are different in structure inside?
It's the same structure.
Oh.
Our canisters are exactly the same. We identify them like this so the customer knows what they are.
Oh, okay.
But if you had to replace a canister and it has a different color label, like this one, no, on the return side, see that one says it's a combination flow homogenizer and pulsation damper, but all these canisters are. They have the same components inside. So if you have to, if the customer damages a can and you have a can available, it's not the right one, don't worry about it, put it on. You can take the stickers off of it and put the right stickers on,
Okay.
you know.
Yeah, that's a...
But they're exactly the same. You don't have to, you know, get an emergency shipment from us of the
That's a good
cans.
thing to know.
Right.
Sorry, when the fuel going to this structure, it first
Right, that one, yeah.
then go pass through here, but sensor is somewhere here. So
Right,
it's just
the sensor is here.
Yeah.
Most of the flow, the majority of the flow goes through the block. Only some of the flow comes down into the sensor, spins the sensor, goes out the sensor, and then the two flows join at this point right here, and they all go through the pulsation damper. They come into the body of the damper, and until it fills up to the top of the standpipe, overflows the standpipe, then goes down and goes back to tank.
So the purpose of this
The purpose of that canister is
to trap the air.
well, no, we want to trap a little bit of air up there, but usually what forms up there are diesel vapor fumes and maybe a tiny amount of air. We don't want air in the system. The reason we do want vapors there is to give a place for the backstroke of the fuel pump. When a little bit of fuel leaks by the fuel pump and it actually goes backwards, it gives it a place to go. The rest of the canister absorbs the pressure spike pulsations that are generated by the injectors and the injection system.
This guy trapped the air, but what does this guy does?
No, that guy doesn't trap any air.
Yeah, but what it does on the inlet?
Oh, well, that comes in, and there's like a tube assembly in there with a bunch of holes in it, and the fuel is coming in all churned up.
It
Okay.
just makes them together.
Well, it straightens it out. It gets rid of the turbulence. It makes the flow what they call laminar. Laminar flow is a smooth flow with no turbulence.
So it smoothen the flow of the fuel.
It smooths the flow out. You cannot achieve perfect, fuel will never be 100% laminar. There'll always be
Because
something in
it's
there.
rushing in.
Right, but we cut it down from tremendous amount of turbulence to very small, almost nothing. Not perfect, but almost nothing, to the point where it doesn't matter when it impacts the rotor and the sensor.
Okay. Okay.
Okay, any other questions?
So these two are not replaceable because the internal structure is different.
Replaceable.
Huh? These two
Exactly
Right, oh
the
yes,
same.
yes, you can take these canisters off, like if your customer drops something on it, or if he sprays it with seawater and it rusts out, You can twist that off. It's difficult. You need a strap wrench and a cheater to get it off. But
Replaceable.
Yeah.
Just that the stickers are different to identify.
right,
So internally they are the same.
Exactly the same.
Identical structure.
all three of them. They're actually
All three of them actually identical
right.
structure.
They're a combination flow homogenizer and pulsation damper. We're using this one only as a pulsation damper, and this one only as a flow homogenizer. We don't care about the turbulence in the fuel once it leaves our sensor.
He asked you what's inside here. What's the inside structure?
It's magic. See if I
It's a secret.
see it. Well, I was the
You
one.
have to leak out your secret.
I kind of developed that from my fluid power background, but there's a, let's call it a membrane in there. There is a tube structure and a membrane, okay? And the membrane absorbs the pressure spike pulsations. How can I say it? When the pressure spikes come back from the engine, they follow the fuel line. And the fuel in the fuel hose is like a carrier for this pulsation energy. When I'm talking now, the air is a carrier for my voice so that it goes from me to you. Well, the fuel is a carrier for this pulsation energy. When you force it through our magic membrane,
Magic.
that energy is used up or dissipated going through the membrane, so that what little is left on the other side of it causes our sensor no problem.
So to make the rating stable.
Very stable. We had to go to this K-series system. I started working at FlowScan about 15 years ago. And right after I came there, we started having problems on some of the installations. They were going to much higher injection pressures from the injectors. And some of these injectors are like, I don't know, 30, 40,000 PSI or more. The reason they went to the high injection pressures is to get finer atomization of the fuel. So if you have a big drop of fuel going through, you put a torch on it and it burns, it makes a lot of smoke because there's not a lot of surface area for it to burn. If you atomize that fuel very finely and you put a torch on it, it's like a flamethrower. The fuel burns instantly, not instantly, but very quickly. There's a lot of surface area from tens or hundreds of thousands of droplets. And when it burns quickly, it burns cleanly. It cuts way down on the particulate emissions. So they were doing that. Our old canisters were fine until that came along. When we had to develop another system, come up with another answer, Wilfred Batts, our chief design engineer, had lots of ideas. Some of them kind of worked, others didn't. I have a marine fluid power background as well as being a marine engineer, and there's an item that we used to use that I thought would work, and we tested it out, and we did hundreds of hours of research at a Bosch test center, and that canister is almost 100% efficient in reducing pulsations. Our old design was very efficient for low injection pressures, 8, 10,000 PSI. But once you started getting up to 15, 20, 25,000, the efficiency fell way off. It wasn't able to do the job.
Ideally, it should be in this way.
Ideally, right. But
If there's a restriction here, can we put it the other way?
you cannot if you put it up top, I won't do it, but if you,
Yeah.
so you never do this. That's a field expediency. If you put it up like this, you're going to have vapor bubbles trapped on both of them.
Or both sides.
It sets up an oscillator effect.
Oh,
And because they both,
Make things worse.
right, air is compressible, so they'll compress at different rates, okay? And it will drive the rotor and the sensor nuts. It will speed up, it'll slow down, it'll read high, it'll read low. You never do this. That's why you can go to about that point there, and that's fine. If you
the
go,
worst at a certain degree.
right, something like that. The pulsation damper, you can rotate it as well, but the more you rotate it, the less air that'll be trapped, the less vapors.
Filter là- Filter là- Is this the same structure as the engine filter?
No,
No?
it's magic. No,
Magic.
it's not.
You're not going to take out the magic.
No, it is not the same as an engine filter.
Basically, it's a membranes.
Hmm?
It's a membranes.
Membrane.
Yeah,
Membrane.
membrane, right.